Alright, hello everyone. In today's video, we're going to be going over everything you need to know about quantum numbers, electron configurations, and orbital notation. This is going to be a fairly long video. I have a lot to explain here and a lot of practice problems, but I do think this is important overall just to kind of go over everything. And of course, you guys can always skip through if you're like, I already know that stuff. You can skip through, watch whatever you need to. So this is going to be a long video. Just a forewarning, but I am going to hopefully cover everything that you'll need to know. Okay, so just to start off about the basics of what quantum numbers are. So they tell us about the estimated location and state of an electron on an atom given a certain set of rules. So basically, when you're looking at a quantum number, it'll look like maybe you're looking at an electron configuration or like a quantum number, or you're looking at orbital notation, which we have over here. It's telling us here's where we think the electrons are, here's how they're going to be shaped, and here's their orientation. And the reason why we do that is because this is what, not a great drawing, but this is approximately what an actual atom looks like. We're always told that an atom will look like something like this, right? Where we have something in the middle, and there's the little rings going around. All right, that was pretty good, not gonna lie. Pretty good circle there. But we're always told that the electrons are kind of just going around in a circle, kind of like a solar system, right? That's always what we're told throughout, like the basic kind of like levels of high school and everything like that. But that's not true. That's just so that it can help us visualize the energy levels and things like that. But this is really what science's best guess of what an atom looks like. So what we have here in the middle is our protons and neutrons, that's our nucleus, and then on the outside it's what we call an electron cloud. The reason why it's called an electron cloud is because that is basically our best guess as to where the electrons are. So electrons move extremely fast, they're constantly moving in many different places, and this is where the word quantum comes from, because quantum is basically we don't know where the thing is because we can't see it. It's not possible for us to measure it. That's where you get Schrodinger's cat, where it's is the cat dead or alive in the box? It's dead and alive. So we call it an electron cloud because we don't know where the electrons are, so they're everywhere around the nucleus within a possible given location, right? Because it's nearly impossible for us to measure it because they're constantly moving. They don't really stop. They go in many different ways, and it's basically our best guess is this electron cloud. But we can zoom in a little bit into the electron cloud in order to determine the quantum numbers to tell us approximately the location of an electron, the shape it's going to be in, and the spin of the electron. So that's what these quantum numbers are doing. They're basically telling us hey, this is science's best guess as to where these electrons are, and you can figure it out. And I think that quantum numbers are really fascinating because, again, we don't know where they are, but this is our best guess. So I think it's a pretty cool concept. So I have some examples here of different quantum numbers that we're going to be dealing with. So I'm going to go work my way from the bottom up. But quantum numbers are the things that we talked about in class and what he has a little sheet of. Maybe I can find it. Yeah, this little sheet here. So we have N, which is the energy level, L, which is the orbital shape, M sub L, which gives us the number of orbitals, given the number of values of ML. And then we have MS, which is the orientation of the electron or the spin, right? So electrons, this is kind of more of a physics lesson, but electrons either move in this direction, which would that be clockwise or counterclockwise? I think that would be counterclockwise. I don't know. I'm always bad with that. I don't know the clock. But they're either moving in this direction or they're moving in the other direction. And that's their spin, right? So the torque, either going up or down, again, this is a physics lesson. You don't have to know this, but that's why the spin is in either up or down, because it's really talking about the torque of it, right? So if you have something that's spinning in this direction, the torque's going to go up or down, and then if it's in this direction, it's going to go up or down. Again, you'll learn this in physics if you do have to take that. I know that bio majors have to take it. Obviously, physics majors have to take physics. And then, I'm not exactly sure what majors end up having to take it, but you may see that. So it's kind of like a little intro to that. And then we have the electron configurations, which is the thing where you have the energy level and then the sub-level and then the number of electrons in the sub-level. So you have 1s1, 2s2, or 1s2, 2s2, 2p6, then it goes to like 3s1, and yada yada yada, right? So you're just going down the periodic table and basically saying, all right, here's the energy level we're in, this is the sub-level, this is how many electrons are in the sub-level, next one, okay? So you're basically going down each sub-level and describing it. And then orbital notation, you're basically doing the exact same thing as the electron configuration, but you're making a little pretty picture with it. So here, with all of these, I did oxygen. So we have the 1s, and we have an orbital that has 2 electrons spinning in different directions. Same thing with the next one with 2s, and then in 2p we go spin up, spin up, spin up, and then we do spin down, right? So I always like to call the rule up, up, down, down, which I'll describe in a few slides from now. But this is basically the things that we're going to be looking at here, right? So that's the quantum numbers we're going to be dealing with. Okay, so the first thing is quantum numbers, right? So this is the thing that, again, we did in class. We talked about this, and he had assigned everyone to kind of, I'll make it in pink so that you know what I'm writing. So he kind of told us to like review it and look it over and everything, but I'm going to go through the chart. I basically just like copied and pasted his chart in here, and I'm going to go through each one and describe it, right? So the principal number of the quantum numbers, that is the distance from the nucleus or the energy level, right? So if I were to say, what was the principal number of oxygen? All you have to do is find oxygen and you figure out what energy level it's in. So it's in 1, 2. It's in energy level 2. So the N would be 2 for oxygen. The maximum value, it technically doesn't have a maximum value, but if you look at the periodic table, it only goes 1, 2, 3, 4, 5, 6, 7. So the maximum number is technically 7, which I have written up there, but technically, again, like there is no maximum value, right? But according to the periodic table, it is 7. So you're not going to see like 9 energy levels, right? So you usually stop at 7. And again, the values go 1, 2, 3, because if you look at the periodic table, you have 1, 2, 3, 4, yada yada yada. You don't have any halves in there, you don't have any zeros. There is no like 0 energy level, because if there was a 0 energy level, there would be no electrons. So first energy level, second energy level, third, fourth, fifth, and so on. I'm gonna butcher this pronunciation, what the hell? Occidental, azimuthal. I thought it was like occidental. I don't know. But L. This tells us the orbital shape, right? So I have over here that when L is 0, it's S. When L is 1, it's P. When L is 2, it's D. And 3 is F, right? So the value of this is N minus 1. So, yeah, this basically tells you like the orbital shape of what you're dealing with, right? So it goes 0, 1, 2, 3, so N minus 1. So if you have your, what did I have? I did the example of what oxygen, which is in the second energy level. So you would do N, which would be 2, minus 1, which would be 1. And then you come over here, you're like, okay, that would mean that it's in the p orbital, and it is. So yeah, and I'll also show you this picture here, right? So this is actually a document from somebody that I tutor, but I have this picture in here that is like the holy grail picture, right? So this tells you where each block is, right? So on this left-hand side here, you have the S block. I always call this the big guy in the middle, because it is. It's just like, and the transition metals are just complete chaos. They don't have any like distinct charges except for like zinc and aluminum, or zinc and silver. But I call this like the chaos box, because it is. But this is the D group, and then over here is the P group, and then you have the F block down here, right? So that's something that you might want to have on your index card if it's a little bit difficult for you to understand. And same with this thing, right? I'm gonna definitely add this on my index card, because no way I'm memorizing this. But yeah, so that tells us the orbital shape. So with S, it's like a sphere. With P, it looks something like this. With D, you're getting like all these different things where it's like, you got something going around in different directions and it looks like a flower almost. And then F, I don't even want to attempt to draw F, but you can look those up if you're interested on how they actually physically look. You'll get a little bit into that in organic chemistry, right? So you'll start talking about like the P bonds and how they have to, double bond with a different P bond and things like that. And you have to count up how many S bonds there are, etc. So you'll get into that in Orgo, which literally one of my favorite classes ever here at RCBC. Totally take it, even if you don't have to. I love that class. Okay, anyways, moving on to the magnetic field, or the magnetic, whatever. So these values are what I like to just say is like, plus or minus L is basically what it does. So if your L is 3, it's going to be -3, -2, -1, 0, 1, 2, 3, right? So you're basically just going across like a little number line with each increment of L. All right. And then the maximum value is plus or minus L, as I said before. You just take L and you do plus and minus of it, and then you go from each side until you get to 0, basically. And what this tells us is the number of orbitals, right? So again, let's look at oxygen. Oxygen, N was 2, and then L would be 1, so we get -1, 0, 1. So the number of orbitals should be 1, 2, 3. Now let's look. Number of orbitals, we have 1, 2, and 3 orbitals for oxygen. So that's good there. And then the spin, it's plus or minus 1, 1/2 for like each electron. Basically, like it, if you have 8 electrons, which would be oxygen, each electron is going to be like plus 1/2, minus 1/2. So that tells you like if it's spinning up or if it's spinning down. But yeah, that it's kind of like hard to describe that with like, when we're talking about quantum numbers. It's more easy to describe that when you're dealing with orbital notation. But I do have a practice problem with this one. It says, provide the quantum numbers for phosphorus and briefly describe what each of them mean. For spin, you don't have to like really give a number for that. You just describe what the spin is and how each electron needs to have a spin or whatever. So you can either pause the video and try this out yourself. I'm going to get into it right now. Alright, so for phosphorus, let's look on the periodic table. There it is. Number 15, right? Number 15. Principal number, we're looking at the energy level. So we have 1, 2, 3. It is in the 3rd energy level. So N is equal to 3. And that tells us that it's in the 3rd energy level. I'm going to just shorthand everything. Okay, and then the next one, also Tuthal. I totally wrote that wrong. Like, it's definitely something else, but whatever. So that is N-1. So L is equal to 2. And this tells us the orbital. So we know that 2, so 0 is S, 1 is P. And hang on, let me check this real quick. Interesting that it would say it's in the D, because it's not in the D orbital. But according to that number, that does mean that it's in the D orbital. Unless I'm doing this wrong. Interesting. So it says that it's in the D orbital according to that. But you can see here that it's not in the D orbital, it's in the S orbital. Or it's in the P orbital. Interesting. I'm gonna write a question right there. Because I personally don't like the quantum number method. It's like not the way that I do things, but I'm just gonna write because that's what it says that it's in. It's in the D orbital, but I can tell from the periodic table that it's technically in the P orbital. So yeah, it's like an interesting method of that. Okay, moving on to magnetic. Since L is 2, it's going to be -2, -1, 0. Apologies for the dog barking in the background, by the way. So this means that it has 1, 2, 3, 4, 5. So this means it has 5 orbitals. And we'll check our answer by looking at the periodic table. So we have 1 orbital, 2 orbital, 3, 4, and 5 to get to phosphorus. Alright, and then the spin, we can just write, like, electrons are spinning up or down, is what I'm just going to write. But yeah, I do highly encourage you guys to take a look at this one, because I'm not 100% sure as to why it would say it's in the d orbital, but if anybody knows, and you would like to let me know, because I actually never learned that until until this semester, so yeah, I was a little bit lost when we were talking about it. Okay, so the next thing to look at is the electron configuration. So this tells us about the quantum numbers, aka the electrons, right? But in like a more like simple term, basically. Like we're taking those quantum numbers that we just figured out and we're putting them into like almost like a sentence, basically. So you're like, here's numbers and letters that describe the quantum numbers, right? So I have an example here, and I think this is sodium, but just to show you that the 1 out in front, or the number out in front of the letter, is the energy level, right? So 1s is the first energy level, 2s is the second energy level, 2p is the second energy level again, and then 3s is in the third energy level. And then the letter, so the S, S, P, S, D, F, eventually we'll get there, is the shape of the orbitals, right? And then the number, the little exponent at top, tells us the number of electrons present in each sublevel. So just to kind of like give you some like terms and stuff here to know, energy level is again like N, right? So it's the number of energy levels present or within that energy level, right? So like 1 is just this first energy level, which is just hydrogen, helium. 2 would be lithium, beryllium, boron. All those elements are in the energy level 2. And then we have 3, all those ones, and then 4, technically, you just kind of skip these over, which we'll talk about, and then you go down here, right? And then orbitals are a space that holds the, oh wait, I skipped, sublevel, is the shape of the orbital. So you have S, P, D, and F. That is your sublevel. And then orbitals is the amount of space that holds an electron. So when it comes to the sublevel, with each shape, there's a different number of orbitals and electrons allowed, right? So in each orbital, you just know that there's always going to be 2 electrons in each orbital. In every single orbital, like drill this in your head. One orbital can have 2 electrons. One orbital can have 2 electrons. One orbital can have 2 electrons, right? So the shape of it tells us how many orbitals that there are. So S has 1, P has 3, D has 5, and F has 7. Again, this might be a good thing to write down in your notes. So for the S orbital, there's 2 electrons allowed. For the P orbital, there's 6 electrons allowed. In the D orbital, there's 10, and in F, there's 14. So again, I'm going to go back to this picture here. When we're talking about the sublevels, you basically just follow the periodic table, right? So let's say that we were doing something like, let's reference this periodic table where we're doing, we'll do bromine. So bromine is about here. yeah. Bromine's here on the periodic table, right? So in order to find that, we're going to go 1s, and there's 2 electrons, 2s, 2 electrons, 2p, 2 electrons, 3s, 2 electrons, or this should be 6 electrons, 3p, 6 electrons, 4s, 2 electrons, and then we go 3d, and I'll show you a picture as to why we go back down to 3. So then we do 3d, and then we do 4p, and then we do 4p, and we only have 1, 2, 3, 4, 5 electrons present in that one, right? So I'm going to show you really quickly why the heck we go back to 3D. All right, so here's your good old Bohr's model. We'll go up to 4. So we'll say this one's filled, this is filled, this has basically filled, and right. So we know that the octet rule tells us that we can only have 8 electrons present in the outside electron, or the outside energy level, right? So what happens if we need to add another electron? Because if we had all of these in the same level, we would end up having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We would have 18 electrons in the outer shell. That would be an extremely unstable state, and the atom will be extremely unhappy, right? It's going to want to remove those electrons. So what these electrons do is that they go to the next lowest, and they just start adding on to there. They just keep adding on until you get the number of amount of electrons that you want, right? So the outer shell is just the S group and the P group, right? So the outer shell is just the S group down here, and then this P group down here. So that's what the outer shell is. But then everything that is here in the middle, in the D group and in the F group, they just move down the next energy level to add on, right? So that there's no instability. Okay. You know, there's a lot of information being thrown at you. A lot of this is just kind of like FYIs so that you can help you like conceptualize it. But again, like it is a lot. So it's a lot to take in, and this video is probably going to end up being like 35 minutes long. So yeah. Let's do some practice with the electron configuration. So I'm going to do one myself, and then I'll let you guys try it out. So we're going to do the electron configuration for arsenic. So let's find arsenic right there. So I can tell right now that this is in the 4th energy level, and it's going to have 3 electrons in its P group. So I know that that's what I'm going to have to go up to, right? So start with 1s1 or 1s2, because that's completely filled. So this group is filled. And then 2s2, this is completely filled. Apologies for the coughing. I'm still recovering from my cold. 2p6, because that's going to be completely filled. And then we'll just keep moving down. 3s2 will be completely filled. 3p6 will be completely filled. And just to remind myself, we're going to the 4th energy level. So we have 4s2 will be completely filled. So right now we're here, 4s. So we know that we're going to have to account for this group here, but remember, this is going to move down an energy level. So it's going to go to 3d 10, because that's completely filled. Right, and you can count that there's 10 electrons because there's 10 elements, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we move on until we get to arsenic, where we have 3. So we have 4p3. And that would be the electron configuration for arsenic. All right, so feel free, this one was kind of like a harder one, but feel free to try out sodium and fluorine on your own. And I'm going to do that now. So sodium should be 1s2, 2s2, 2p6, and 3s1. That's just me going off of my memorization of the periodic table. But let's check. So 3s1, that would be it, right? So all you have to do to check yourself is to look at the last number there, and you're like, all right, well, 3s1, we're going to 1, 2, 3, and the first one, yeah, that's sodium, right? So that's how I always check myself. And then we're going to do fluorine, which is in the 2nd energy level. So it's going to be 1s2, 2s2, and 2p, not 7, 2p5. Let's check. So let's go to 2p. We're going 1, 2, 3, 4, 5, and we landed on fluorine. So that is our answer. So those are all good. Okay, So let's move on to the shorthands of the electron configuration, because this is something that he briefly touched on in class. So I'm going to quickly kind of go over these. So basically what shorthands do for the electron configuration is that sometimes electron configurations can be long. So let's say we're doing like polonium. Polonium? Alright, polonium? Yeah, polonium. Sure, that's how we pronounce it. The electron configuration is going to be 1s2, 2s2, 2p6, and you get the story. You're going to have to go through every single one and the whole thing's going to end up being like a paragraph, and it's going to be a pain in the absolute butt to have to do that. You're going to be you're going to get to like energy level 3, and you're going to be like, all right, I'm sick and tired of this. So what the shorthand does is that it helps us to make it shorter, but you're still getting the same result. Like, you're still getting the same answer, and you can figure out what element it is and everything based off of these shorthands, right? So the first one is a noble gas shorthand, which is probably like one of my personal favorites. I really like it. It's kind of fun to do. So with the shorthand noble gas, what we do is we do the noble gas before in little brackets, and then you do the rest of the electron configuration. So I did the example of magnesium. So let's look and find magnesium, right? And we'll figure out what the noble gas before was and the rest of the configuration. Magnesium. There she is. Beautiful number 12. So what we're going to do is we're going to backtrack, right? We're going to go, all right, what's the last noble gas before this, right? So magnesium, we're going to go over, all right, that's sodium. We're going to kind of loop around, go back. Neon. Neon is the one noble gas that is before magnesium. So we're just going to do this. We're going to write Ne with the brackets, and then we're going to do the rest of the configuration. So from Ne, the rest of the electron configuration, it just goes 3s1, right? Which I have written down here, or 3s2, sorry, because we're at the second one. So it's going to go neon 3s2. That would be your answer right there. We'll do some practice on that, and I'll show you some examples, right? But that's how you would do it. And then for valence cell shorthand, you're just doing the S and P subshell. So just as a reminder, if it loads, the S is over here and the P is over here. Again, that is your valence shell, as we talked about before, of the last energy level, right? So the example here is selenium. Selenium is right here. Again, you're going to get through this, and you're going to get to this sub-level, or this energy level, and you're going to be like, oh my god, I'm sick and tired of writing these. It's going to take you forever, and you're going to hate it. So we do the shorthand of it with the valence shell, where we just do S and P. So if we move over to the S, we can see it's in 1, 2, 3, 4. It's in the 4th energy level, so we're going to fill this one. So it's going to be 4s2. We're going to move over. It's going to be 4p, 1, 2, 3, 4. Which we have written here. 4s2, 4p4. And that would just be your answer when you're asked for the valence shell shorthand. So let's go into some practice with that. So practice of electron configuration shorthand. So I'll go through the first two, and then I'll challenge you guys to do the last two, or do it however you want. You can pause now and try them yourself, or you can even skip if you're feeling confident. Do whatever you like to. So we're looking at boron first. Boron. Oh, that one's easy. So what does it want? It wants the noble gas. So the noble gas before boron is helium. So I'm going to write that down first. Good old helium. And then we're going to move down from helium, right? So helium, and then we have 2s2. 2s2. And then after that, we just have 2p1. Alright, so now we're going to look at the valence shell shorthand for lead. I wrote down here, I wrote Ng and Vs and Ng and Vs. I wrote down here what those mean. It's just noble gas, and I shorthanded the shorthand, basically. So we have the valence shell for lead. Lead, oh my god, yeah, I don't want to do this whole thing, so I'm glad I gave myself the shorthand for this, because this would be a absolute pain in my, to do this. So we're looking, right? We're going to do the shorthand, which means we're just doing the S group and the P group. So this is in 1, 2, 3, 4, 5, 6. It's low. All right, so 6, So we're going to fill this one. So it's going to be 6s2. Then we move down. 1, 2. I gave myself lead, right? Let me just check. All right, lead. I have a very bad memory. And we're going to go 6p2 because there's only 2. Oops, that's not a 6. 6p2. All right, again, so I'm going to challenge you guys to do this one yourselves, but I'm going to go into it right now, so pause the video if you'd like to try it out. All right, noble gas, shorthand for bromine. Bromine, where are you, bromine? That's like the hardest thing is finding where they are. All right, we're doing the noble gas shorthand for it. So the one before that is argon. So you move down, work back around, there's argon. Right, so we're going to write that down. AR for argon, and then we're going to do the rest of the electron configuration, right? So from argon, we're going to start here, and we're going to do these two. So it's in 1, 2, 3, 4. So 4s2, 4s2, and then move down. We're going to do 1, 2, 3, 4, 5, 4p5. That would be your answer. And then we're going to do the valence shell shorthand for cobalt. Cobalt is, where is cobalt? Ah, my favorite. It's down here, I think. Now, can we find it? This is going to take me a hot minute to find cobalt, I guess. Oh, there it is. Oh my gosh. Okay, I was like, where is CO? Where is CO? All right. So for the valence shell, remember, we are only doing the S and the P group here. So remember that this is 3D. This is in the 3D group, right? So we're only going to have to deal with this because we don't go to the 4P group. We're just in 3D. So we're only going to look at this. This is in 1, 2, 3, 4. So it should be for, just 4s2. And that would be the valence shell shorthand, because that is the valence shell of it. But yeah, so that would be your valence shell shorthand for that. Yeah, so that is the practice for the shorthands. We have one last thing to cover. Is this just a blank page? All right, that's just a blank page. All right, so last thing that we're going to cover is orbital notation. So orbital notation is pretty simple. Once you get down your electron configuration, orbital notation should be 100% easy. You're going to have no problem with this. Since this is a multiple choice test, you're probably not going to be asked to draw the orbital notation, but you're probably going to have to pick from different orbital notations, or you're given an orbital notation, you have to write down what it is, right? So if you could draw it, then you could do the rest of those steps. It's as simple as it is. I'm getting tired. We're 33 minutes in this video. All right, I'm going to try to wrap this up, right? So carbon, let's look at this example, right? So carbon's one would look like this, where you have the 1s is one orbital, 2s is one orbital, and then 2p has 3 orbitals in it, and you're going, 1, 2, 3, 4, 5, 6. So the steps that I always take to do this. So I always write out the electron configuration, or I just kind of put it in my head because my brain is very good at remembering numbers. So I usually just kind of keep it up in the noggin, but definitely write it down. I'm going to be writing it down during the test just so I can double check myself, because sometimes you got to do that, right? So I write out the electron configuration, and then I draw the sublevels as boxes. And remember, one box is one orbital. So this is an orbital, this is an orbital, 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 right? And as you remember from the last slide, we know that each sublevel has a different number of orbitals. So the S sublevel has 1 orbital, the S sublevel again has 1 orbital, the P sublevel will have 3 orbitals, and then the D has 5 orbitals, so you'll have 5 boxes, and then the F has 7 boxes, or 7 orbitals. So after you draw the boxes, you're going to place your electrons. So the number of electrons is going to actually be equal to your number up here, right? So if we're doing arsenic, there's going to be 33 electrons that you have to draw. I know it's going to be a pain in the butt, but you got to do what you got to do, right? So you place your electrons, and remember that you're doing up, up, down, down. That's the rule that I like to say. So let's say that we have something that, this is like a 3D, we'll say. Let's draw out that there's 5 in there. 1, 2, 3, 4, 5. So let's say that you have 7 electrons in this 3D. You're going to go 1, 2, 3, 4, 5, 6, 7. So you're going up, 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 down, 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 right? So that's the rule that I always follow. So you always want to put the spin one direction, and then you do the next direction once your sublevel is completely filled. So I write down here, must all go up in a sublevel, then down. And that just has to do with like the kind of like the stability of it. So if you have electrons that are all spinning in the same direction, they're going to be much happier and much more stable than if you have them spin all different kind of crazy directions. That's going to make them unstable. So it's better for them to be spinning in a singular direction, and then you can do the other direction, right? You want them to be stable first, and then you can go and do the things that make it a little bit unstable. Alright, so now to do just some practices on this, and then that will be the end of the video. And again, very long video, so I appreciate if you watched even any of this. But the orbital notation practice, right? So for the first few questions, you're going to draw the orbital notation for sulfur and boron. And then the last question is you're going to name the element that has the following orbital notation. And I'll give you a little tip and trick for doing that, right? So let's talk about the first one. Again, you can pause and try them out yourself, but I'm going to go through them now. So for sulfur. Sulfur, we have an electron configuration of 1s2. Let me relook. So we're in the 1, 2, 3, third sublevel, so we're going to go up to the third P. So 2s2, 2p6, 3s2, and then we're going to stop at 3p because we're going to count how many electrons we have. We have 1, 2, 3, 4 electrons. Then from there, I'm going to draw my boxes, right? So this is the 1s group, this is the 2s, we're going to draw 2p, we have 3s, and we have 3p. Make sure you're giving yourself enough room, because I'm not giving myself enough room on these ones, but it's okay. 3s, this is 2p, 2s, this is 1s. Alright, so for the first one, we're going to go up and then down, up and then down, up, 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 down, down, down to make our 6, up and then down, and then for the last one, we're going to go 1, 2, 3, 4. And that would be our orbital notation. Alright, now for boron. We're going to do a little bit of a simpler one. So the the electron configuration for boron is 1s2, 2s2, and then 2p1. We can see that because up here we fill this level, and then we fill this level, and then we just have 1 in the 2p. So let's draw that out. This one is really nice and easy. 1s, 2s, this is 2p. We're going to go up and then down, up and then down, and then we're just going to go up here. So it only has 1 electron in the 2p. Okay. Moving on to the last question. What element has the following orbital notation? So you're probably going to sit there and maybe be like, all right, let me write out this whole electron configuration, right? You don't have to do that. All you have to do is look at this last sublevel, and that will tell you exactly what element it is, right? So let's think. What element will have the ending of an electron configuration as 3D? 1, 2, 3, 4. 3D4. So let's go to the D block. We're at 3D. We're going to go 1, 2, 3, 4. Right now it's looking like chromium. So I'm going to write chromium. I'm going to circle it. Now to check my answer, what I do is I like to count up the electrons. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And if that matches 24, chromium, that would be our answer. Alright, so that is everything for this video. I do appreciate you all watching. Be sure to definitely do some practice problems with this one. I'm not sure if this is going to be on the quiz or on the exam because he doesn't have a list of everything that's going to be exactly on it. But this will definitely help you out in like the future when it comes to Orgo, and even in Gen Chem 1 or Gen Chem 2 to kind of help you visualize these electrons and everything. So thank you all for watching, and I hope you have a great rest of your day, and yeah, have a good one.